Hi, my name is Charles Raz, and I worked on the Markov chains project this quarter with Anthony Sanchez. So if we recall from the mid-quarter presentation, a Markov chain is a stochastic model describing a sequence of possible events in which the probability of each event depends only on the state attained in the previous event. And the Markov property is as follows. Given the current state, xn, any other information about the past is irrelevant for predicting the next state, xn plus 1. And Markov chains have transition matrices that have embedded transition probabilities, and we denote them Pij, probability of going from I to j. So the probability that x plus 1 is equal to j, given that xn is equal to I, and all this other previous information is just denoted probability of going from I to j, Pij. And applying the Markov property, we see that all this previous information can be discarded. So probability that x plus 1 is equal to j, given xn is equal to I, is the probability of going from I to j, Pij. So we will use an example called the social mobility chain as we learn more things about Markov chains. Consider that there are three different social classes, one being the lower class, two being the middle class, and three being the upper class. And we let xn be the family social class at the nth generation. So xn takes three values, and we have the transition probabilities here. Probability of going from class 1 to 1 is 0.7, 1 to 2 is 0.2, 1 to 3 is 0.1, etc. And on the left here, we see that this diagram has the arrows that which indicate the transition probabilities between each social class. And what we can do is turn this diagram, this system, into a transition matrix, which will be very handy, and we'll see later. But essentially what we do is start on the left-hand side at class 1, and then we say probability of going from class 1 to class 1 is 0.7. So we drop 0.7 in the upper left-hand corner of this matrix, and then similarly, probability of going from 1 to 2 is 0.2, so we drop that just to the right of that. Probability of going from 2 to 1 is 0.3, so we drop it right below 0.7, and we fill out our matrix this way. And so it's important to note that the rows of transition matrix sum up to 1. It's just a property of transition matrices. And we'll see that the transition matrix is very useful for various computations, and it allows us to see the nature of the Markov chain after a certain number of steps and the long-term behavior of it. So at this point, we can ask a couple questions. One, what is the probability that your children are lower class, given that your parents were middle class? And two, do the fractions of people in each class approach a limit? Does this Markov chain converge over time? So what is the probability that your children are lower class given that your parents were middle class? So we know that our parents' class, x0 is equal to 2, and that our children's class, x2 is equal to 1. But the intermediate step, which is our social class, can take three possible values, 1, 2, and 3. So the probability that x2 is equal to 1, given that x0 is equal to 2, is the probability that x2 is 1, x1 is some value k, given that x0 is 2. So what we do is we sum over all the possible values of k. And what we do is we apply our notation from the previous slide, and we see that this is the probability of going from state 2 to k times the probability of going from k to 1 over all possible values of k. So starting at k equals 1, we see the probability of going from 2 to 1 is 0.3, and the probability of going from 1 to 1 is 0.7, and then similarly 2 to 2 is 0.5, 2 to 1 is 0.3, and we just drop these values in here from the matrix, and we get 0.21 as our answer. And then we notice that there's nothing really special about x0 and x2, so we can generalize these two-step problems as follows. Probability that x2 is equal to some state j, given that x0 is I, is the sum over all possible intermediate steps k, probability of I to k times the probability of k to j. So it turns out if we want to find the two-step transition probabilities, all we need to do is square our transition matrix. So the probability of going from I to j in 2 steps is just our transition matrix squared, and we have those values on the right. So furthering this discovery, we introduced the following theorem. So the m-step transition probability is the mth power of the transition matrix P. So the probability that xn plus m equals j, given that xn is equal to I, is the mth power of our transition matrix because we're taking m steps here. And the Chapman-Kolmogorov equation helps us understand why this is true, but we're not going to spend too much time looking at this because we have a lot of material to cover. But essentially what it's saying is that if you want to go from state I to state j in m plus n steps, you have two independent paths here, I to k in m steps and k to j in n steps. This is just a little bit of an extrapolation from what we saw in the previous slide. So do the fractions of people in these classes approach a limit? Does the system converge? So there's a few different ways that we can find this. You could just raise the matrix to a very high power, kind of get a sense of the transition probabilities by using a calculator, or you could use more advanced techniques and take the limit of p to the n as n approaches infinity. But what we're concerned about here, and sort of the whole goal of this lecture, is to understand the convergence theorem, which relies on stationary distributions. So we suppose I, A, and S, which is a bit complex, and we're not going to have time to go through all the prerequisites of this hypothesis, but our social mobility chain does in fact meet this hypothesis. So we're mostly concerned about the fact that as n approaches infinity, the nth power of our transition matrix converges to something called pi y. So we introduced the notion of a probability vector, which we denote Q. We multiply our transition matrix on the left by this vector Q, and this vector Q has the initial distribution of probabilities. So if there are k states, our transition matrix is a k by k, and since we're multiplying on the left, our vector Q is a 1 by k row vector. So for the social mobility example, suppose that Q1 is 0.5, Q2 is 0.2, and Q3 is 0.3. And these are the probabilities, the proportions of people in each social class respectively. So half the population's in social class 1, 20% in 2, and 30% in 3. So we multiply our matrix on the left by our Q vector, and we get 0.4, 0.47, 0.32, and 0.21. These are the proportions of people in each social class after one step. So Q is a stationary distribution if Q times our matrix P is equal to Q. That is, the distribution at time 0 is the same at time 1. And if this is true, we can apply our Markov property, which is a memoryless property, and it says that this will be the same distribution at all times. Since 1 is the same as 0, at time 2, it'll be the same as time 1, which is the same as time 0, so it'll be the same at all times because the system essentially resets. So we denote stationary distributions as pi. We say that pi times p is equal to pi. And we can think of this as an eigenvalue with lambda equal 1. So if we recall from linear transformations, especially in matrix representation, we say t of x is equal to a of x is equal to lambda x. So here, pi times p is equal to lambda times p, but lambda is just 1. And it turns out that 1 is an eigenvalue of all transition matrices, which is a cool property. So we denote the general two-state transition probability as this matrix on the right here up top. And we note that the rows sum up to 1, just like they did in our social mobility example. So we've written the chain in this way so that the stationary distribution has this following formula. So pi 1 is b over a plus b, and pi 2 is a over a plus b. These are some nice ratios that we're working with. And we can check that pi times p is equal to pi by multiplying pi 1, pi 2 by our matrix up top. And the algebra below shows us that indeed pi 1 pi 2 times our matrix is equal to pi 1, pi 2. So we apply this pi p equal pi to our social mobility chain to find the values of pi. So pi1, pi2, pi3 times our matrix is equal to pi1, pi2, pi3 because we want to preserve that equality, and we get the system of equations up here on the right. And then we simplify it a little bit and we add a very important equation to this system, which is pi1 plus pi2 plus pi3 is equal to 1. Because these are, we're looking at a whole population here. So we have to account for everything. So it has to equal, the probabilities have to equal 1. So what we do is we solve the system algebraically, and we end up getting pi1, pi2, pi3 are equal to 22, 16, and 9 over 47 respectively. And we note that these indeed do add up to 1. It's also worth noting that the columns of our matrix give the coefficients of the system. So the rows of the matrix sum up to 1, which means that the columns of this system of equations will sum up to 1. And to conclude, the convergence theorem tells us something very, very important about a certain system that we're modeling. So systems converge to a nice equilibrium if they have these required characteristics, which our example does. So it tells us what's going to happen to a Markov process over time. And what it's saying is that the probability of being in each state will eventually become fixed. So multiplying our 22, 16, and 9 over 47 by our transition matrix, which by the way could be raised to any power, will result in the same probability vector, same distribution we had initially. So it doesn't matter where you start out, the system will be the same in the long run. And as Markov chains are really highly applicable to a whole bunch of real world problems, this convergence theorem tells us the long-term nature of the system that we're modeling, which is a very important thing to know when you're modeling something. So thank you so much.